On the left, we have the function f of x equals negative square root of x plus 7 plus 2, which is a transformation of this parent function y equals square root of x. And we're asked to graph the inverse of f of x. So we're asked to graph the inverse of this function that has already been transformed. So to do this, we're going to apply the transformations first to create this f of x, and then we're going to swap the x and y to create the inverse. Now on your right, we're told that g of x equals the inverse sine of x over 3 plus pi over 2, and we're asked to graph g of x. Here, we're going to take the parent function y equals sine of x, create the inverse function by swapping x and y first, and then apply the transformations. So the sequence of steps is going to be different. And the reason is, with f of x, we're starting with the regular function. With g of x, the transformations are applied to the inverse function. And we're all aware from a very early age in our math careers that order matters. Recall the acronym PEMDAS. By the way, PEMDAS is false advertising. Written as is, one would think that multiplication always comes before division and addition always comes before subtraction. That is not true. Multiplication and division, the order thereof, is predicated on going left to right. Same with addition and subtraction. This would really be a better way to write it, indicating that multiplication and division, addition and subtraction are treated the same depending on which comes first as we move left to right. So the remainder of this video, we're going to talk about why this is so. Why is this order of the sequence of steps different? On the left, when we're asked to take the inverse of this function transformed from the parent, versus asking to graph the inverse function, which is transformed once you get the inverse function by swapping x and y. Okay, folks, here's our first function, f of x. It's rewritten here on this diagram. The parent function, y equals square root of x, is written here. If you put x equals 4 into this parent function, square root of 4 is 2, square root of 9 is 3. Now, we're going to take these transformations and apply them to the parent function. Transformations, you could see it's a horizontal translation to the left. By 7, recall the inside of a function lies. It says plus 7. That means we're going to subtract 7. So in each of these x values, we're subtracting 7. 0 minus 7 is negative 7. 1 minus 7 is negative 6, and so forth. With the y values, first we're going to multiply by negative 1. That's a reflection over the x-axis, and then we're going to add 2. So here we go. Let's look at this. When y equals 2, we're going to multiply by negative 1 and get negative 2. We're going to add 2 to get 0. Here, when y equals 3, we're going to multiply by negative 1, get negative 3. We're going to add 2 and get negative 1. Now, to get the inverse, we swap the x and y values. And that gives us the inverse of this f of x function. Again, apply the transformations first, then swap x and y. And in terms of graphing it, you could see here is our original function, f of x. You could see that the normal f of x starts at the origin and heads out towards the first quadrant. Because of that negative sign, we're going to have a reflection. We have a translation, 7 units to the left, and then it's going to be translated up 2 units. And here's our inverse function. If you graph these coordinates located in this table, and you could see that the graphs are reflections of each other over the line y equals x. Now, for our other function, where g of x is already an inverse function, inverse form, and we have transformations of the inverse function, we're going to do things differently. First, we're going to take the parent function y equals sine of x. we're going to create the inverse function by swapping x and y, and then we're going to apply the transformations. We're going to take the original functions, y equals sine of x, create the inverse function by swapping, and then applying transformations. Here's what we're not going to do. We're not going to apply transformations to the original sine function and then swap. This is incorrect. Okay, here we go. Again, folks, our goal is to graph this function right here. Y equals inverse sine x over 3 plus pi over 2. Here's our sequence of steps laid out. We're going to start with the parent function y equals sine of x. We're going to create the inverse function by swapping x and y, and then we're going to apply the transformations. So on this slide here, we see the original sine graph. And you recognize that it starts at 0, and at pi over 2 it's at 1, and it continues. Now folks, notice I've limited the domain. The domain of this function y equals sine of x from negative pi over 2 to pi over 2, and that's because, as we know, when we're dealing with trigonometric functions that are inverse, their domain is limited. So recall the inverse sine is limited to this region here, like so. That is where inverse sine is located. And as a result, we're going to limit our domain from negative pi over 2 to pi over 2 in this discussion. Now notice, folks, I went further. I also looked at the points pi comma 0 and negative pi comma 0. And that's because these extra points, although ultimately they will not be part of our final answer, helps me draw the curvature. Sometimes if we just have these 3 points, I get confused as to what's concave up, what's concave down. But the fact that eventually the normal sine graph hits pi comma 0, and it also hits negative pi comma 0, I include those as ghost points to help me maintain the curvature. Okay, so here's our original points that are going to be part of our final answer, and these are the ghost points. Again, part 1 is to flip these x and y, and we also flip the axes. When we do that, we could see that negative pi over 2 comma negative 1 becomes negative 1 comma pi over 2. The point at the origin doesn't change, and this point that was negative pi over 2 comma negative 1 flips to negative 1 comma negative pi over 2. So we've switched the axes. Here we go. This is negative 1 comma negative pi over 2. There's the one at the origin, 1 comma pi over 2. But we included these ghost points. We flipped this from pi comma 0 to 0 comma pi. We flipped this from negative pi comma 0 to 0 comma negative pi. Folks, this is y equals inverse sine of x. And the correct portion is the black dotted portion. And again, this extra portion is included to help me with the curvature. Now that we've created our inverse sine graph located here on the upper left, with these points indicated, these extra ghost points, now we're going to apply our transformations. So here's our final equation. I went ahead and expanded it, including our A value, our B value, our C value, and our D value. So as we could see, this is going to be a vertical stretch. Let's start inside. This is going to be a vertical stretch by a factor of 3 with no horizontal translation. There is no vertical stretch or compression, and there's going to be a vertical shift, positive pi over 2. We're going to apply each of these to our points. Here we go. That's our B value. We take our x, we divide by the B value, and then we take the opposite of what we see here as the C value. It's 0, so it's not relevant. And we do that for each of our points in addition to our extra points. With respect to the y value, Multiplying by 1, it does not affect things. We're going to be adding pi over 2 to each of our y coordinates, including our extra points. And when we do that and we graph it, this is our final graph. So here, this is our solution in black. These are not part of the solution, but they help us draw the graph in terms of knowing what the concavity is going to be. And here on Desmos, this is the final graph, and you could see it does match our graph. You could see it crosses the x-axis right there at -3, and there's 0 comma pi over 2, just like we have here. Here is a summary slide of what transpired in this video. On the left, we are asked to graph the inverse of f of x. We create the transformed function first, and then we swap the x and y to create the inverse. On the right-hand side, we're asked to graph g of x, which is an inverse function that has been transformed. Therefore, we have to create the inverse function first before we apply the transformations. Again, on the left, transform the function first, then get the inverse. On the right, we have an inverse function that's been transformed. So we have to create the inverse function first and then apply the transformations.